Hi everyone, thank you so much for joining in. So today we'll be hosting Robert. I'm not sure of the pronunciation of your second name. Maybe you can give us
Boedigheimer.
Boedigheimer. Let me just not even try it. So we'll be hosting Robert. He's been working in the industry for, I think, since the 90s. That is
Yes.
so long. So he was even in the industry before most of us were born. So he'll be talking about cryptography. A fun fact about him, he's both a Pluralsight author and also an MVP. But the best thing something that I really liked was that he holds a black belt in Taekwondo. Like, he's not just tech, he's Taekwondo. Like, oh God, that's amazing. So I think you can start, Robert.
Okay.
He'll be taking us through Cryptography 101.
Okay, so like we said, we're going to talk about Cryptography 101 today. So the important part of this is the concepts is what I want to focus on. I'm going to happen to show all of the code in C# and .NET Core, but most languages and frameworks that you use will have good libraries for cryptography. So if you're not familiar with C# and .NET Core, at least all the concepts should be something that you should be able to take advantage of. I do have the slides and the code. So I have two versions of the code. I have the .NET Core version, and I also have the .NET full framework version. They're very, very similar. There's not much that changes between .NET Framework and .NET Core. I'll point out a couple things, but again, you'll have access to all of the code. I have a link to the slides and the code at the end. So as you said, there's some of my background information. That's my Twitter, my email, and my blog. So we'll jump right in. So for a background, cryptography is the science of keeping your messages secure. And it's important when you think about cryptography to understand what it is you're going after. So there's really four major things that you might want to use cryptography for. When we talk about cryptography, generally people think about confidentiality. They want to protect the data from being read. So when you say cryptography to someone, they immediately think of encryption and they automatically think of confidentiality. They have a secret they don't want people to see. So that's obviously a big part of it. But we also use cryptography for integrity, and that's where we want to verify that data has not been modified. So I'll show you a couple examples of that. We use it for authentication, where we want to identify and validate a particular user. We also use it for non-repudiation, digital signatures, where we want to make sure that a sender can't deny that they sent a message later. We can prove that it was sent by a certain person. In .NET, all of the classes I'm going to show you are part of this system.security.cryptography namespace. So when you think about security and when you think about cryptography, there's a lot of considerations. So the first one is, again, what is your goal? Confidentiality, et cetera. As I go through the talk, I'm going to refer back to those goals. It's important that you know the goal you're after so you're sure you're picking the right technology. You need to think about how much your data is worth. How long do you need to keep it secured? Only for a couple hours, or it's something that needs to be secured for decades? You need to think about your primary threats. So I work on an e-commerce site. So I have a web server sitting on the internet, and I treat that web server like it could be compromised. So at any given time, there could be a flaw in my web server. Someone could take complete ownership of the web server. So I need to, that's my security stance. I act like that server, people can do anything they want to it. So in that case, I need to think about, obviously, in transit. So I use HTTPS for that. We'll talk about that a little bit. I have to worry that someone could gain access to my configuration files. So we'll talk about key storage. Someone could also do a dump of memory. So there are ways to take everything that's in memory and write it out to files if they have ownership of my web server. And the issue with that is in .NET, if I have passwords or keys or credit card numbers stored in strings and variables, if those have not been garbage collected yet by .NET, those would be part of those files. Someone could modify my web pages, so I have to understand that even though the page is written, it's possible they could deploy different pages. They could also reverse engineer my assemblies. So I'm going to show you some examples. If I have a key hard-coded in a string, in .NET, my C# compiles to an intermediate language. Someone could use ILDASM or other tools. They could reverse that back to pseudo source code and be able to see all of my secrets and all of my keys. So I just need to think, and we'll go through examples of what are the threats for your system so that you think like an attacker and come up with how you're going to protect yourself. I have company security policies, so my company has rules about things I'll have to follow. I also have regulatory compliance because I take credit cards. We have to do PCI compliance. So all of those policies and compliance regulations control some of the things I can use for cryptography. I also want to think about layered defenses, and I need to think about how many are enough, right? The only safe computer is one powered off in a lead box in the corner, right? That's not very helpful. We need to be able to actually run things, and we need to trade off the risk versus the business value. If you take nothing else from this talk, don't try to write your own cryptography. So I've heard people before say, you know, I'll write my own algorithm, it'll be a secret, nobody will know it, it'll be a lot more secure than anything else that's available. History has proven that that's extremely unlikely. As I said, the frameworks have good cryptography built in if you're picking good tools and libraries. They've been vetted by security experts. Even people who do cryptography a lot make mistakes, so they're checking each other's algorithm and work, and with open source that helps us know that the algorithms are implemented correctly. So don't try to write your own. I'll mention this in .NET because you'll see it in some of the code. I'm going to talk about AES, which is an encryption algorithm. There are various classes in .NET like AES Managed, AES CNG, and AES Crypto Service Provider. In the .NET framework, these suffixes mattered. So if I picked the AES Managed, that meant that that class was written completely in likely C# in a managed language. If it ended in CNG, that meant that the .NET code was just a wrapper around the cryptographic next generation that was built into newer Windows operating systems. And if it ends in Crypto Service Provider, that just means it wraps the old crypto API, which is available on old Windows systems. So again, if you're doing .NET Framework, it may matter which one you pick. If you need FIPS compliance and such, you can't use Managed. In the .NET Core world, it really doesn't matter because in .NET Core, they rewrote all of those classes to wrap the underlying operating system libraries. So if you're familiar with .NET Core, it just lets you run .NET on Windows, Mac, and Linux. And because it runs on those different operating systems, they chose to just rewrite all of these various classes. They all wrap the operating system libraries. If you are going to do .NET Core and you choose an algorithm, it's important to go to this bottom link because not every class is available on every platform. So if you choose a class in cryptography, maybe I'm testing it out on Windows, I want to deploy it also to Linux, just check that chart first. You don't want to get all the way down and developed and then find out that that class isn't available on the platform you're going to deploy on. We'll jump into the first part of cryptography, which is hash functions. So people talk about hashing and encryption like they're the same thing, and they're not. We're going to talk about hashing first. And what hashing is it's a one-way function. It's really easy to compute in one direction. It's very hard. Hopefully, if your algorithm is good, it should be impossible to reverse. So in other words, I have this string on the left-hand side. If I compute a hash, I'm going to get some result. If I changed even a single character over here, this hash value should change. Also, it doesn't matter how big this value is on the left side. No matter how big this is, the hash size will always be the same fixed length. That length just depends on which algorithm I use. So I'm going to use SHA-512. This will end up being 64 bytes of data all of the time, regardless of what my data was. People often call this a data fingerprint or a digest. and it's used for both integrity and authentication. So again, it's very simple. Hash functions will take data and go this direction. If I have a hash value though, we want it to be impossible to reverse. So given this, I shouldn't be able to figure out this. In .NET, the abstract base class is called hash algorithm. You'll see a lot of different hashing algorithms in industry. I've listed some of them here that are built into .NET. I put a strike through, so if you know Troy Hunt from Have I Been Pwned, he looks at data breaches. A lot of data breaches, if you read how they happen, people were storing passwords using MD5 hashes. MD5 is just not considered secure anymore. So that's why I put a strike through. You shouldn't be using that anymore. The same with SHA-1 algorithms. They were used for a long time. They've also been broken. PCI regulations say that you should not be using any SHA-1 hash algorithms. The SHA-2 family of algorithms, there's a few of them. The 256, 384, and 512, that's just the number of bits in the result. SHA-2 is still considered secure. It's what most people are using in .NET today. There's an organization called NIST that does encryption algorithms. They decided that because SHA-1 was broken, they wanted to get ahead of the game in case SHA-2 had some flaws. So there is a SHA-3 family of algorithms. They had a contest, they chose a winner. The problem for me, it's not built into .NET yet. And so from a company perspective, I want to use things that are built into .NET. I don't want to go looking for third-party libraries because then I need to worry about, have they been vetted? Are they secure? So I just want you to know there are SHA-3 algorithms available. SHA-2 is still considered secure, so you're fine with this. I just wanted you to know that those are out there. There's also keyed hash algorithms. So not only do I take the data, I'm also going to use a key when I do the hash, and we'll see why that's important here shortly. So let's look at our first example. Code. So again, this code is in .NET Core. It's in ASP.NET Razor pages. So I'm not going to spend much time on how the pages actually function. I'm just going to focus on the cryptography. So here I have a simple string, and I want to compute the hash for that string. So what I do, I'm going to use the SHA-512. That's one of the classes in .NET Core. I just create an instance of that class. Something you'll notice in .NET, as developers, we use strings, we use ints, we use longs. The cryptography libraries in .NET want to use a byte array. So the first thing I need to do is take that string and convert it into a byte array. There's lots of different ways to do this. There's lots of encoding schemes. I'm going to show you UTF-8 is pretty popular. UTF-16 is as well. But what this UTF-8 get bytes does, it takes my string and converts it into a byte array. So this won't really matter. The examples I'm showing you, I'm the only one using the hash, so I can choose what I want for encoding. Later on, if you start doing encryption and you're working with a partner and you're encrypting things and they can't decrypt, one of the things you have to agree on is, how am I going to encode? How do I take a string? Because if I use UTF-8 and you use UTF-16, it's not going to work. So I use UTF-8 here. Now I have a byte array. I just call compute hash, and I get back a byte array that represents that hash value. So I want to be able to show this on the screen. So I'm going to go over to the code here, or the web page. You can see here's my string, and here's what it hashes to. Because I wanted to show that byte array, I can't show a byte array on a web page. I need to convert it into something. There's many ways I could do that. I chose to display it in hex. So there's a class in .NET called bit converter. I can pass it that byte array. And what it does is it represents each byte as hex. So if you're familiar with how hex works, it's just another number system. So you can see here it would look like this, and I just decided to take the dashes out. So again, I compute the hash, I convert it into hex, and you can see here is my hex value. If I look at the code again, if I were to uncomment this line, you can see the string is a lot bigger. It'll come up with a different hash value, but the size will be the same. Again, the output of this hash is always the same size, regardless of how big your input is. That's one of the important things for hash functions. So that's interesting. Where would I use such a thing? I created this thing called tamper-proof query strings. So if you've been to websites before and you look on the URL and it has customer number equals 123. If you've ever gone up there and you could change that URL, if you put 124, it's very likely you see some other customer's data. That'd be a problem. And the issue is that we're using relational databases usually. We use sequential numbers. I see that customer number, it's right on the URL. If I can modify that URL, I have a problem because you're letting customers see other people's data. So we're going to use hashing, and we're going to do integrity. So hashing is around integrity. That's our goal. So what I want is I'm going to create the query string I want. I'm going to put the hash of that query string on the URL. That way, if someone tampers with it, we will notice. Again, how that would look. So I have a hyperlink here. I wanted to pass this query string, A equals 1, B equals 2, C equals 3. If you notice, I have a hexadecimal hash as well. So what that'll do is if someone comes up here and says, I'm going to try to change that to 2, I'm going to get the hash value, and then on the server, I'm going to recompute the hash of what was sent and compare the two. And I'll notice that the client tampered with it. I obviously will never do this in production. I'm not going to show you on my production website detailed error messages. That just helps the hacker figure out what I'm doing. But for the demo purposes, I wanted you to be able to see what I was doing. If you think like an attacker, if I were an attacker and I saw this, I might figure out that's a hash. I might just try to delete that. Okay, that doesn't work. So I want to think like an attacker, work through my threats, try a few things, right? If I were a hacker, the next thing I would try, well, let's look at some of the code first and then we'll see how to attack it. Here's the query string I wanted. So one thing you notice is I used to be able to hard code my links. Now I have to use code, right? In order to compute this hash, I can't just say ahref and give this hyperlink. I actually have to compute a hash of it. So I wrote this common compute hash function. So let's take a look at that. It's very similar. You saw this is how we were doing it before. Here's our compute hash line like we did before. And then I just let you output it as hex, or base 64 is also possible and popular. I will show you that later. So very similar to code to what we had before. And then when the receiver receives it, again, for the demo, I'm just doing it directly in the receiving page. In real life, I would put this somewhere more common so all of my pages can do it. But the page that receives that data is just going to validate it. It's just going to take off my hash. It's going to pull off the query string. It's going to recompute the hash of whatever was sent and compare it to what I had on the URL. And if they don't match, you see we get the exception. So let's go back to thinking like an attacker. If I were an attacker, I would notice you're using a hash. I could do the same thing you did, right? I can look at the length. I can figure out it's SHA-2. I can figure out it's 64 bytes. So it's a SHA-512 hash. I have the same hashing algorithm you have. I want to put A equals 2. So I could go and compute this just like you could. So I'm not going to go through that whole demo, but I could compute the hash. I could come back here and add my hash value, and I would be able to break your system. So why? I'll tell you it won't work, and I'll tell you why it won't work. If we go in the code here, I added one more layer of defense. Instead of using a normal hash algorithm in this case, I'm using a keyed hash algorithm. So in this case, not only do I take your data, I'm also using this secret key. So I've made it that much harder for the attacker, right? We talked about threat modeling. We talked about layered defenses. Now someone who wants to attack my tamper-proofing, they have to actually be able to compromise my web server, read my assembly, disassemble it, and they would find this key. So again, for a demo, here's my key. I'm going to talk about key storage briefly. Key storage is hard, right? Storing this key securely on a public-facing web server that I said someone could own is a problem. We'll talk about a few techniques, but for the demo, here's my key. But at least it takes the very simple hackers. So first of all, people that don't know anything about computing and cryptography, they're not going to be able to come up here and figure out what I'm doing. There's, normal people, non-developers are not going to be able to come up here, change this, and figure out how to get around my hashing. Simple hackers that think they can go compute a hash will also find they can't get in. So we've just made it harder and harder, right? Lock my house, I have an alarm on it. A burglar comes down the street. If I have a gate, a dog, an alarm, big spotlights, a camera, they're more likely to move to the next house, right? I'm trying to make it harder by adding these layered defenses. So that's a practical use of hashing. It shows how we want to use it for integrity, and it shows why using a key is a good idea. Another place we use hashing is hash passwords. So I did undergraduate research in college on password cracking. And back then, I was working on a Unix system. The people who created Unix were trying to decide how they should store passwords. And they looked at cryptography and they noticed if they used hashing, because hashes are a one-way function, if they took your password, hashed it, and stored that, no one would be able to reverse it, right? You can't reverse a hash function if it's good. So they said, we're going to store your hash password in what was called etc password file. So this was just a text file that's put on Unix. And they were so confident, which is the next problem. They were very confident that we know hashes can't be reversed. We're just going to let anybody look at that text file. So if you had any account on that system, you could go pull the password file. You could see every user ID on the system, and you could see their hash passwords. They weren't doing very good threat modeling. So the problem was, yes, I can't reverse a hash. But back then, about 60 to 80% of all passwords were just dictionary words. So the attackers figured out if they could hash every word in the dictionary, then all they need to do is compare the hash. So for instance, I can take secret. I can compute the hash of secret. Then I just need to compare that hash to every password in the file's hash. And if I get a match, I know it was secret. So I didn't break the algorithm, but I was still able to gain access to the password. So I'll show you what that code would look like. So I went into the password file. Here's one of the hashed values. I just took a guess at what it might be. In real world, this is where I would take an online dictionary and I would compute the hash of every word in the dictionary. These days with social media, I would also go on your Facebook, Twitter, LinkedIn, anything you have online, which is a lot. I would look for your dog's name, your spouse's name, all the things you like to do. Like I like Taekwondo, I like Led Zeppelin, anything that you might like, I'm going to guess might be your password. So if I were to run this page, even though I can't reverse that hash, you can see it turns out that that hash was for secret because I was able to guess that might have been one of them, and that happened to be what it turned out to be. So you just need to think again like an attacker. So that wasn't great. So the good team, security people, said, we need to do something better. So the next step they took is what was called salted passwords. So they said, we'll create some unique random data for each user. So each user has their own salt value. They then take your password and your salt value and compute a hash. And they store that in the password file. So they now have your hash password and they keep your salt in there because next time you come, they need to know the salt that was used. So what that did is, as an attacker, if I pull that password file, now I can't just compute the whole dictionary and everything else, all the hashes, and attack every password. Now I need to do it one at a time. So I have to take a user, take their salt, and run through and compute all those dictionary words. So it's made it harder for the attacker. They can't just pre-compute hashes once. They have to do it now for each user. So it's made it slightly harder, right? The bad news is it doesn't help an individual password. So if you think about it, again, I'll pull the password file. I'm going to look for admin or administrator or somebody that has an account that can do everything on the system. I'll take their salt and pre-compute the dictionary with their hashed password, all these values. So it's made it harder for me to attack the whole password file, but it didn't actually help me protect an individual password. So let's look at what that looks like. The code will be very similar. I'll mention, and you need to generate some salt. So for each user, you need to have a salt value. So let's diverge for a minute here and talk about random data. So if you know how computers work and you know random, they say they have a random number generator. Most random number generators on computers really aren't that random. They're very poor at choosing truly random numbers. You need to make sure that you use what's called a cryptographically strong random number generator. And in .NET, it happens to be this class. So whatever framework you're using, make sure it says it's a cryptographically strong random number generator. Okay, so this is as good as we're going to get in .NET. Computers aren't perfect. They're a set of instructions, so it's still hard to get random data. If you're familiar with Cloudflare, it's a major internet provider. They need random data too. So what they did is they set up in California, I think they've got hundreds of lava lamps. So if you've seen lava lamps before, when they heat up, the lava just kind of flows within the lamp. They take a picture of their lava lamps and digitize that and use that to get random data. Because again, we need outside of computers to get true randomness. So that just happens to be what they use, which is kind of interesting. Again, in .NET, we're going to at least use this cryptographically strong class. The hashing looks the same, but in this case, not only am I hashing the data, I'm also hashing that salt value. So let's look what this looks like. So here's the string. Here is the random salt that was generated. Again, I would do this once per user and store it in the file, but for the demo, I'm recreating it each time. So you can see here was the original hash. Each time, I've also added in the salt. If you think like the attackers again, I said it doesn't help you protect an individual password. So they also started adding in this secret key. So again, they just decided we're going to generate some random data and use that. So now we use your data, your salt, and a secret. So now again, we've made it harder. The attacker now can't just find your salt. They have to be able to break into your page, figure out what the secret is. Then they would be able to start pre-computing hashes. Okay. Real world hashing today for passwords uses functions like this. So if you've heard about bcrypt, bcrypt is pretty popular. It doesn't happen to have a version in the .NET framework, at least not built in. So there's another function called pbkdf2. It's actually a password-based key derivation, which we won't have time to get into today, but it can also be used for hashing. So this is what people actually use today if they're hashing passwords. And they do it because this adds what's called a work factor. So I said I'm a Led Zeppelin fan. Obviously, I'm never going to use that for my password, but in this case, that's my password. I've got some salt. Here's the function. So what's different about this is you set the workload. So in other words, I want this to run this, in this case, 100,000 times. And what I'm trying to do is I'm trying to make it intentionally slow. And then again, I'm doing that, so it's hard for the attacker. If I happen to use 100,000, let's say today I run this on my web server on modern systems, and that takes about a half of a second. That means the attacker has to wait a half second for every word in the dictionary. It just makes it harder for them to set up their attack tables. So you need to choose a number that's a good trade-off. I don't want to make it take 10 seconds because when you come back to log into my website, I need to do the same thing. So I need to trade off how slow I want this to be. But just be aware this is what people do today. And then as computers get better, they'll just make this count go higher and higher to get protection that they need. So that's hashing. Now we're going to start talking about encryption. So there's some terminology that is in history that I need you to be familiar with. So the first one is plain text. That's your original data. Encryption is the process of obscuring that data. When I run encryption on the plain text, it's called ciphertext. When I want to get back to my original data, it's called decryption. And the cipher is the algorithm I use for the encryption and decryption. So this is used for confidentiality. So when you talk about cryptography, people usually think about confidentiality and they usually think about encryption. The first class of algorithms for cryptography we're going to look at are called symmetric algorithms. So I have my plain text. I'm going to encrypt it using a secret key. I have my ciphertext. I can run it through decryption. So the important part about symmetric is encryption and decryption use the same secret key. Then I can get back to the original plain text. People who try to attack this, if you're using a good algorithm, they're not going to be able to break my algorithm. Instead, they're going to brute force and try to do every single key. So we'll talk about key sizes later. You want to have a key size that's large because an attacker's just literally going to try the first key, see if it works, then the second key. So you want to have a really large key. There's a number of different classes in .NET for symmetric. DES has been around for a very long time. It's not considered secure anymore, so don't use that. What you'll mostly see in industry is the AES, the Advanced Encryption Standard. This is sanctioned for US government work. They had NIST again had a contest, and the winner was the Reindahl algorithm. So that's what we're going to do. We're going to talk about AES in our examples here. In .NET, the symmetric algorithms are called block ciphers, the ones that we're going to look at, which just means it takes your plain text. If I pick a block size, maybe 256 bits, it's going to take that message and break it into the first 256 bits, do encryption, then it takes the next block. That's just how the encryption algorithms work. If you think about it, my message is not going to magically fit in the last block. In other words, I have a certain number of characters. There's going to be some extra space in that last block. So it supports padding. So I'm going to use this ISO. This will pad the end of that last block with some random data, and we'll see why that's important. In AES, there's also many different modes. I'm showing you two of them here. The ECB mode just says take the first block and encrypt it, then put it aside. Take the next block and encrypt it, put it aside. We're not going to want to use that, and I'll show you why. We're going to use CBC. What CBC says is we'll encrypt the first block of data, and we'll use the result of that as some randomness to add in when we do the next block of data. So just when you think about cryptography, the more randomness you add, the harder it will be for somebody attacking you to see patterns. So again, we'll use CBC mode. I'll show you the example of why you want to do that. So if you think about CBC, if it's using random data for every block, what does it use for the first block? Well, it turns out it uses what's called an initialization vector. And all that is it's a piece of random data that will be used to encrypt the first block. It does not need to be a secret. So after I run AES, I'm going to have my ciphertext. I'm going to send you the ciphertext, and I'm going to send you the IV. You need to know what that is in order to do the decryption. It turns out that the IV does not need to be secret. So if I can send the encrypted data to you, I don't need to worry about the initialization vector being seen. I do, however, never want to reuse it. So every time you do a new symmetric encryption, you need to have a new random initialization vector. If you don't do that, you'll start to see patterns again. So let's look at what the code looks like here.
Before we check out the code,
yeah,
there's a question. So
sure.
To everyone in the meeting, if you have any question, you can just type it in the chat or raise your hand. So there's a question. I've seen many encryption algorithms use letters between A and F and numbers between 0 and 9. Is there an encryption algorithm that only uses numbers?
So what they actually are doing, it's not the algorithm, it's how they're encoding it. So they're using hex. So what you're referring to, the 0 to 9, A to F, is using hex. And that just works out for how they do bytes. I could choose to make this just the result. I could have represented, so if we go back to, and this is true for all of them, but I'll show you in the hashing. If I go back to the hash algorithms we looked at, if I go back to the very first one, I have a byte array. You can't show bytes, it's binary, right? I can't show that on a web page and stuff, so I need to convert it into a string. I chose to put it into hex. That's just a typical thing people do with cryptography, and that's where you see that 0 to 9, A to F. Hex is a good representation because I'll get a little nerdy with a byte is 8 bits. And a bit can be either 0 or 1, so there end up being 16 different values. And so hex is just a good representation of that because it has 16 letters and numbers to represent it, if that makes sense. I could choose instead to say, I'm going to change my byte array and represent it in decimal and just use numbers if I want to. It doesn't turn out quite as clean. So it's possible. So it's not the algorithm, so to speak. It's the how I'm encoding it. Does that make sense? It's how I'm choosing to display the binary. Yeah.
Yeah, thank you.
Yep.
I think you can
okay.
Continue.
So if we look at, let's look at the symmetric here. So first, let me run it. We'll just do, if I encrypt it. So this is what's important. If you watch, every time I encrypt it, even though it's the same plain text, the ciphertext is changing. And it's doing that because I'm using the CBC mode, and each time I'm using a unique initialization vector. If I do the decrypt, we'll see it got back to where I started. So let's see the code for this. In the encrypt method, both my encryption and my decryption are going to use AES. So I just wrote a common function to create that cipher. So I talked about the suffixes before. You know, in these classes exist, but they really don't make sense in core anymore. So I'm just going to use the normal AES. I listed the defaults. The key size is 256. The block size is 256. I chose to use the random padding. Here's my secret key. Again, I won't do this in production. I don't want to just store it in a page because somebody could gain access to my source code and see that, or see it in Git if I accidentally check that in. So again, we'll talk about that later. But I create a cipher. Every time I create a new instance of AES, it creates a new initialization vector for me. So automatically it's creating a new random initialization vector for me as long as I'm creating a new object. I chose to use base 64 just to show you another view. So this is base 64. So if you ever see stuff that ends in 2 equals, that's base 64 encoding. So I showed you hex before, there's base 64. Those are probably the 2 most popular ways people will encode their binary to display it. But again, I need to create the encryptor. We saw this before. I'm using UTF-8 to take the string into a byte array. Again, if I'm going to work with somebody else, we got to make sure we're using the same thing here. And then this is the actual encryption. Now I have byte array ciphertext, and I chose to base 64 that again. I could have done hex as well, but so the good news, if you step back, if you look at this, we've got really strong cryptography. AES is a well-known algorithm. I'm using a good key size. I know .NET Core people have reviewed this implementation of AES, so I have confidence that this is hopefully doesn't have flaws in the implementation. It's been tested a lot, and it's really not a lot of code. So if you looked, all I need to do is create, you know, in my company, I'll create a function called encrypt data. You pass it a string and your key. It's really not a lot of code to get a lot of security. Again, that's why you don't want to try to write your own code. So I want to show you again, even though AES is strong, if you'd made the wrong choices, so I'm going to stop my web server here. I'm going to change that to use zeros for padding and ECB mode. And again, ECB is just doing the block by block encryption, but it doesn't do the randomness and the initialization vector. So if I run my web server again, if I were to go back and run that page, so what's important, you'll notice every time I hit encrypt, this is not changing. That's bad, right? If you follow the history of cryptography, once people start to see patterns like this, they can start learning things about your algorithm and potentially your keys and be able to break. If you're familiar with the Enigma machine used in World War II, it was used incorrectly in some ways that caused it to not be as random as it should have been. And the Allies noticed those patterns and were able to break that, even though it should have been strong cryptography just because they weren't using it right. So again, AES is solid, it's considered secure, but if you use the wrong modes, you can actually cause problems. So that's symmetric. The problem with symmetric is really the key distribution. So if I were to go into the participant list and pick one of you and I said, I want to send you a secret today, the problem would be if I want to use symmetric, I have a secret I want to give you, but I need to share the secret key with you, right? How do I share the secret key with you? Well, I'm back to the same problem I had before. So they came up with a class of algorithms called asymmetric algorithms. So with these, what they do is each person creates their own public-private key pair. And then if I were to go on the participant list and pick one of you and said, let's send to each other, you would put in the chat your public key. It's fine to let anybody see your public key. People put them in their email signatures, their LinkedIn profiles. You want to have a way that people can trust that it's really your public key. I will warn you, I don't love people putting it as an email signature because email's completely insecure. Anybody could read it, modify it. So let's talk about maybe LinkedIn. If I wanted people to communicate with me, I could put in my LinkedIn profile. Because LinkedIn uses HTTPS, I can trust that you get my right public key. Once you have my public key, you take the plain text, you encrypt it with my public key, you now have ciphertext. No one can decrypt that, including me. Even though I just encrypted it, if I just have ciphertext, I can't decrypt it. The only thing that will decrypt it is the corresponding private key. So the receiver keeps their private key secret, obviously. They're the only one who can decrypt things that are encrypted with their public key. So they use their private key, decrypt it, and get back to the original plain text. So that's how asymmetric works. It's great, right? The problem with it is it's about 1,000 times slower than symmetric, and it can't be used for large amounts of data. So it solves the key distribution problem, but it adds a couple problems that we'll talk about as we go. There are different algorithms. We're going to focus on RSA, one of the most popular ones. So let's look what that code would look like. Oh, by the way, when you get the code, I have a page in here that will generate your symmetric key for you. So you can look at how the code works. Again, it uses the random number generator. I have the same thing for RSA. I have a page that lets you create your RSA keys. So if we look at what the encryption looks like, I'm going to call my common function, which just uses RSA. In this case, I just hard-coded the person's public key. So I just read that in. And then here's the code. This should look really familiar, right? I need to take the string, convert it into a byte array. I call the encryption. It's important with RSA, there's different padding schemes, just like we saw for AES. You want to use this one. The PKCS1 is not considered secure anymore, so make sure you're using this padding. I do the base 64 to display it again. So again, if you look, That's really not a lot of code. So I've now got asymmetric. If I trust your public key is yours, it's very simple for me to send you secure data in .NET in a way that I know only your private key can decrypt. So that's asymmetric. Where would you use asymmetric? So one good example would be if I took credit cards on my website. I talked to you before and said, I think my web servers can be compromised, right? I need to allow HTTPS traffic to them. If it turns out ASP.NET or IIS in my case had flaws, somebody could break my web server and gain access to it. So it's hard when you think your web server could be taken over. Where could you possibly store a symmetric key that's safe? I really can't. If I used asymmetric instead, I will generate an RSA key pair, a public-private. If I put the public key on the web server, I don't need to worry about somebody stealing it. So I put the public key on my web server. I put my private key inside behind my firewall. Again, this is only meant for small amounts of data. So for my example, I'm going to have a web page where you can type in a credit card, encrypt. Now I can take this ciphertext. So I used my public key is on the web server. Now I can take this ciphertext stored in the database, whatever. The only system that should have the private key is tucked away inside my firewall. So a hacker from the outside has to do a lot of work to get inside my firewall and to this secure system. But on that secure system, it could read that ciphertext and do decrypt because it has the private key. So that's a good example of asymmetric makes sense because I had a small amount of data. I can use public-private key pairs. It's still just my own stuff, but I can put the public key on the web server, so I don't need to worry that somebody will see it. If you work with credit card processors today, typically the credit card processor will generate a unique RSA or whatever kind of key pair for asymmetric. They'll give you the public key, they keep the private key. In that case, no one in my entire company can actually decrypt that number. As soon as I get that credit card number, I use that public key. Now, the only person who can decrypt it is the credit card processor. So anything on my system, you can't compromise anything to mine that would give you access to that once the encryption has been completed, if that makes sense. So that's a good example of asymmetric. So we're going to bring all of this together. All the things we've talked about so far are used for digital signatures. So the idea with a digital signature, if I picked one of you again out of the participant list and I wanted to negotiate a contract with you and I want to do it all online, I need a way to take this contract, send it to you. You want to make sure that the contract was not modified, nobody changed any terms, and you want to prove that it was me who sent it. So that is the integrity, means it hasn't been modified. The non-repudiation is knowing that it came from me. So let's look at the picture because this will make sense. If I'm going to send it to you, by the way, digital signatures by default do not provide confidentiality. So I don't have to use encryption for this. For this example, I just decided to do all of it. So I want to send you a contract, but I don't want somebody to be able to read it. So if we walk through the steps, I'm going to do the asymmetric encryption exactly like I did before. I'm going to get your public key and do the encryption. And now I have ciphertext. So now I know the only person who can decrypt this is the person who has the corresponding private key. The way the digital signature works, you compute a hash of that ciphertext. Now I have the hash value. Now this is the digital signature part. I encrypt the hashed value with my private key. That becomes the signature. So now I can send you the ciphertext and the signature. Well, how does that work? Well, when you receive it, you have my public key. So if you trust that that's my public key, you'll be able to prove that it came only from me. So let's take a look at that code.
Before we go into the code,
sure, yeah.
There's a question. If I hack your application, can I get access to your private key?
So in the example that I'm giving, where I have right here, if you had access to, like, if you took over my web server and you gained access, so I use .NET, my C# gets built into DLL, an assembly. If you could get on my web server and download that assembly, you can use ILDASM. It will show you hard-coded strings. So if I had a variable like, you know, this, I would, if I were an attacker, I'd be looking for .keys or passwords or whatever. They would be able to see this. So like I said, I put it in here for the demo. We'll talk about key storage later, but that's why I didn't want to use symmetric to do the encryption. That's why I wanted to do the asymmetric. So that example I just showed you with the website encryption, that's why I want to use an RSA public key, because even if somebody gained access to this and they did the reverse assembly, all they have is a public key. It doesn't help them do any decryption, if that makes sense. Does that answer?
Yeah, I think so.
Okay.
Yeah.
Okay, so let's take a look at next example of a digital signature. If I have a hyperlink, and let's imagine I have another partner that I want to send data to over the internet via a hyperlink or a URL. Here is my secret. And then if I go over on the URL, I'm also appending my signature. So let's look at what that code looks like. I'll go into the sender here. So it's a little more complicated than the other examples, but not too bad. Again, to do the encryption part, I need your public key. So here's their RSA public key. In order to sign it, I need my private key. So this happens to be my public and private key together. So I'm going to start by creating a cipher like I did before using my sender key. So this is what I'm going to use for doing the signature. This is the one I'm going to use to do the encryption. So here's my super secret credit card. I do what I did before. I need to take the string and convert it to a byte array. This is the exact same encryption we just looked at. I can see I'm using the wrong padding there. I do the encryption like I did before. So now I have encrypted ciphertext. I do the hashing just like I did before. I compute a hash. Now I have the byte array for the hash. This is the digital signature part. I take my sender cipher, which is my private key. I tell it to use SHA-512 and tell it to create a signature. Now I have a byte array. So I have two different things. I have the encrypted contract. I have the digital signature. And I chose to use base 64. I could have used hex. And because I decided to put it on the URL, because I'm transmitting it to them on the URL, I use URL encoding just to escape if there's any special characters. And again, that's a lot of power there, right? That's not a lot of code to get everything we just talked about. Now I'm sure that nobody read it. That's the confidentiality with the encryption. You make sure nobody modified it. That's the hashing. And you make sure that it came from me. That's the digital signature. So kind of everything we've talked about comes together in one demo. All of that stuff is how digital signatures work. Next thing we'll talk about that uses a lot of cryptography is HTTPS. So if you host a website, you should be using HTTPS today. HTTPS is going to encrypt all of the traffic between the browser and the web server. So how it works is, as a website provider, I create a public-private key pair. I'm going to give my public key to what's called a certificate authority. So one of them that's free today, Let's Encrypt, I've used. So I generate a public-private key. I send the public to Let's Encrypt. Let's Encrypt will verify that I own that website. Then they do a digital signature. So they have now signed my public key and give it to me as a certificate. Browsers know these well-known certificate authorities, they're called. So they know which certificate authorities they want to trust. So they say, we trust Let's Encrypt. So anything that Let's Encrypt gives out in a certificate, browsers trust. So if you think through what happens, HTTPS uses TLS as the underlying encryption scheme. The browser will connect to the web server. The web server will give it its certificate. The browser will use the digital signature verification. So if I use Let's Encrypt, browsers know the public keys for Let's Encrypt. They're hard-coded basically inside the browser. So the browser says, I trust Let's Encrypt. It uses Let's Encrypt's public key to prove that Let's Encrypt was the one who signed it, so it trusts the certificate. It takes my public key out of the certificate so that it can encrypt data to me. So we talked about asymmetric. Asymmetric is not good for a lot of data. So instead of encrypting the actual data with asymmetric, the browser will choose a symmetric key to use just for this conversation. So it generates a random symmetric key. And there's lots of different algorithms. Typically, it will use AES. It will encrypt that symmetric key with the server's public key. So now it can securely send that symmetric key over to my web server. Now both of them have the shared secret key. They'll use symmetric encryption because it's very fast. So again, you can see everything kind of come together here. We've got digital signatures, we've got asymmetric, we've got symmetric. That's how cryptography is practically used for major websites. Talk about key sizes. So we'll talk about symmetric AES has different key sizes. I talked about in symmetric, they don't try to break AES because they usually won't be able to do that if you have a good implementation. They need to literally try every possible key. I could have used 128 bits. The difference between 128-bit and 256, it's not twice as hard. If you do the math, it's exponentially harder to go through every combination of 256 bits. So just use the largest key sizes you can use. The performance difference is milliseconds. You want to make sure things are secure. We talked about key storage. I don't have enough time to go into all of the options. It really depends on the environment you're in. You could use Azure Key Vault if you're in Azure. There's lots of different ways. I try to avoid it. So in my case, I know I needed to encrypt a credit card. But if I used symmetric, I would have had to store a secret key on my web server, and I already said I'm concerned somebody could attack that and gain access to it. That's why I did the public key. So I'll admit to you, in cryptography, this is the worst part, right? How do I securely store a key on a public-facing web server? There's lots of different techniques you can try to do. ASP.NET had an encrypted section of web config. So I could have stored that key in my web config and then actually used RSA encryption so the actual web config value would be encrypted. So that's better than putting it right in the code. However, if an attacker gains access to the box, ASP.NET in code will automatically decrypt that. So it's not perfect. Again, there's no perfect way to do key storage. You're going to have to look at where you deploy, what environment you're in, and where you're going to be able to put that to at least make it hard to get to, or use the public key so you don't have to worry about it. So in summary, again, don't try to write your own cryptography. Whatever language or framework you're using has good cryptography libraries, hopefully built in. So use those. Use hashing if you're trying to validate integrity. So again, focus on your goal. I see a lot of people think, oh, I'm going to do passwords, I should encrypt them. Well, hashing is a better choice because it's a one-way function. So go back to the goals at the beginning. Are you trying to get confidentiality? Are you trying to get integrity? Once you know what your goal is, it helps you figure out, should I be using hashing? Should I use encryption? Use symmetric algorithms because they're much faster and they do much more data when you need to encrypt, unless you have special needs. So if you need to do a digital signature, use asymmetric. If you have to do a key exchange, use asymmetric. Think about your threats and make sure you're choosing the proper countermeasures. So think like an attacker so that you can come up with ways to make your system more secure. I do have a Pluralsight course on this that's about 2 hours long, Intro to Cryptography. It uses .NET full framework code, but again, the concepts are all similar if you're interested in that. These 3 books in the middle, if you want to really understand how AES encryption works, These books are very detailed on all of the math, and they explain all the bit shifting, all of that stuff. I've tried to read them before. I'm just not that interested to know exactly how AES works, right? There's cryptographers who know how that works. The math gets a bit beyond what I want to tolerate. I did read those books though, because I skipped over the detailed AES, but I read their comments on how you should use AES, like what modes should you use. So those are still worth looking at. If you're interested in the history of cryptography, these are two good books. So if you want to see Caesar cipher and how it got attacked, and then how Vignette cipher came, and just the progression of good versus bad teams, right? How did people attack things? How did people secure stuff? These are really kind of fun books on the history of cryptography, places that went wrong, people who died because they thought they had good cryptography and they actually didn't. So sometimes it's really important that you're doing things right. So some of that history is really interesting. If you have any questions, I don't know what happened with my slide there, but that's my Twitter. That is my email. That's my blog. This is the link to the slides and the code. Again, all the slides, and then you have both the .NET framework, the full framework 4.8, or you have 3.1 .NET Core implementations of everything you've seen today. So that's all I had. If anybody had any additional questions.
Okay, maybe you can go through the questions in the chat. Then if you have any questions, you can either type them or raise your hand. The raise your hand button is the high five, the palm that you can see on your screen. Yes. Okay.
So I can't pull up the chat, so I'll have to have you.
Yeah, I will be reading for you. Okay. Can you encrypt with both public and private keys?
So can you encrypt with both public and private? So they're both usable. So I'll do it this way. It's a little faster. When we talked about asymmetric, normal, you would use public key. So normally in asymmetric, you're sending to someone else, you'll use their public key. But you did notice when I did digital signatures, I was encrypting with my private key. So both of them can be used for encryption and decryption. The public and private are just inverses of each other. So when you're doing signatures, you would use your private. So you can use both, but let's say I just picked one of you out of the list. If I said, hey, I'm going to encrypt something and I'm going to use my private key on it. If I encrypted it, it would work. The problem is anybody could decrypt it, right? Because all of you would know my public key. So it's good for signatures. I wouldn't want to use it for encryption just because I'm supposed to keep my private secret. If I encrypt with my private key, all of you should have my public key. I want to make that accessible, so it wouldn't help at all, if that makes sense. But encryption works with both, right? Either public or private. You just have to know which one you're using in which case. Typically, again, when you're sending to other people, you're just using their public key. Digital signatures is the one place you'd use your private to encrypt. Does that make sense?
Yeah, it totally does.
Okay.
The other question is, which is the best encryption algorithm?
That is a tough. Answering best is always hard. I guess, with ones that I know are still solid and secure. So I follow a lot of cryptography people just to know which algorithms are good. I personally use AES for symmetric just because I know it's used by a lot of people. I mean, it's very common. I know that it's been vetted. I know that it's still considered secure. There's lots of other algorithms. When AES ran the contest, there was Blowfish, Twofish. I mean, there's lots of people that write cryptography, right? And as I was saying, don't try to write your own. You'll see somebody say, I've got this great new algorithm. It's brand new. I don't release the algorithm, so nobody knows what it is. There's a thing called Kirchhoff's principle. Never trust an algorithm that needs to be kept secret. The only thing that should be secret are your keys. So I use AES. It might turn out that the answer inside your company, they might say triplet DES is better. I choose AES. like I said, there are other algorithms, but I'm going to go with ones that are built into .NET that I know are solid, sanctioned, and people that I trust say is still secure, if that makes sense.
Yeah, that makes sense. So maybe we can have, if you have any question, we have at least 5 more minutes. So you can just unmute yourself and speak up, or in the next 1 minute, or we can call it a day.
Thank you for sharing. I would like to know, is cryptography different for cloud security?
So the question was, is this different for cloud? Shouldn't be. You'll use the same techniques and the same kinds of algorithms. Where you would store your keys might be different. So I talked about like Azure Key Vault, but the actual algorithms, whether I'm running this on my own systems, my own web servers, or if I deploy those web servers to the cloud, all the same choices, all the same algorithms. So it really shouldn't make any difference. It might turn out, when I talked about .NET Core, if I chose an algorithm in .NET Core, and I know that eventually I'm going to deploy it on Linux, maybe in the cloud, I need to make sure that that class is available on Linux, but cloud itself doesn't really change any of the stuff that we talked about today as far as how you encrypt it or which algorithms to use.
And another question is,
Sure.
For one who wants to learn cryptography, what should they be looking at? What are the like areas they should be learning in cryptography?
If I were starting brand new, I would get a hold of trying to find a good book that, I mean, obviously I have this course, we have what we talked about today. I would focus first on which, let's start with what's the problem, right? Are you trying to do maybe password storage? Get into hashing, and then I would go look at, I would start digging into the documentation on, trying to pull up the hashing stuff here. I'd start digging into this, right? This is what the PBK DF2 or something like bcrypt. Generally, I liked these books. So the very first place I started was actually this Applied Cryptography by Bruce Schneier. Still very active in security. So if you just said, I want to understand cryptography better, I'd start with this book. It's a little older. Some of these are a little bit newer, but he goes through all the fundamentals of how you want to do cryptography. Don't spend time, don't feel bad if you read it and you get into the AES and the math and the bit shifting. If you don't care about how AES is implemented, that's fine. I skipped over those parts. But starting with a book like that, I've also just read Practical Cryptography in Python. I don't have it listed here yet. I just finished it. That's very modern, and he talks a little bit about how things are implemented, but it's more how you should use cryptography. Where do people make mistakes? What are the right algorithms to use? So that would be a good example as well. I'll pull it up here. So you can get it from Amazon or wherever. I just happen to click on some site, but this Practical Cryptography in Python is pretty recent, and actually I got a lot of things out of it, even though I've done cryptography for a long time, and it's not too thick, so it won't take too long to read. But I would recommend one of those if you want to start. Anything else?
I think we're done with the questions. I'm not sure if there's anyone else.
Very good questions today, by the way. Thank you for asking and participating.
Thank you so much. Thank you also for joining in. Yeah, it's been a pleasure. I am sure we've all learned a lot. So maybe I can just call on to one last person to probably just conclude. But I'm not sure who I can call out to. Let me just conclude on my own. Next time, I will have one of the audience members to give a shout out to you. So thank you so much for joining in. It's been so insightful. I am very new to cryptography, and I've learned quite a lot. I never knew how hashing is done before, how you can be able to even get a digital signature. So thank you so much, and
you're welcome.
I'll see you next time.
Okay, thank you.
Okay, thank you everyone. I will be sharing the recording online on YouTube later on this week, so be sure to check it out. Thank you and have a great evening, a great day to you, and see you next time.